about conformal field theory, or CFT. I prepared a set of lecture notes, which will be presumably updated if there is any, if I find mistakes. Find them in this website, which I didn't correctly that it would fit on the board. Later on also on the website, presumably. Okay, so what is this about? So conformal field theory is an interesting area at the intersection of mathematics and physics, so I think it's particularly suitable for audiences like this. So where it comes from is, so you probably heard about quantum field theory, which is a famous and very successful framework in theoretical physics, which was used with huge success to calculate many things that we observe. However, it's also famously difficult on rigorous grounds. It's still an open problem, more or less, about how to do that. People tried for many decades, but there is particular corners of quantum field theory which describe systems with more symmetry. Those things are kind of more. In those setups, you can go further and make the stuff more rigorous, and conformal field theory is one of the instances where this happens. So this is a kind of, you can go as far as actually to make some rigorous definitions and put things on some solid background, solid mathematical framework. Another thing could be topological field theories or supersymmetric theories, but we will focus on conformal field theories. So that's the introductory introduction. So I sketched this. Maybe I should have done it bigger, but anyway, like the framework of conformal field theories is related to many things. Probably I forgot some. So there is like, on the physical side, it's famously related to statistical models and solid-state physics to describe systems, many statistical models at critical temperatures, but it's also absolutely unavoidable in string theory. It's one of the central things in there in some sense. It's related to the well-studied ADS-CFT correspondence. I won't discuss most of this. This is just to draw a picture to see to what this thing connects. On more mathy side, it's related to representation theory, algebraic geometry, also famously finite groups and modular functions. And in between these two things, there is a thing called moonshine conjectures. And so there was sort of an unexpected connection between the theory of finite groups and the theory of modular functions. And the clarification of what was happening and why there is a connection is ultimately coming from CFT, you can say. So that was one purely mathematical framework in which this thing was kind of successful. Yeah.
So you said monstrous moonshine.
Yeah. Okay. Well, no, I in general moonshine conjectures, but monstrous moonshine is for the monster group.
Yeah.
There's like a bunch of things. There is like Mathieu group. But I won't be talking about that. This is just, to say some fantastic words and then not mention them anymore. So that means let's start with describing what this conformal field theory is, or what conformal symmetry is. So I should say that because of this unique thing that this lies on a boundary between these two fields, I had to decide on how to present this stuff. So I decided in the end to do it in a sort of rigorous, half rigorous way. So it will be somewhere in between math and physics indeed. And the hope is that both mathematicians and physicists will be able to carry something away. So let's see if I'm successful in that. If you feel that I'm very unsuccessful, then let me know and I will try to adjust stuff. So let's maybe start with conformal group in algebra. And then in the second paragraph we will sketch the definition of this thing, but so far let's just do some purely geometric and algebraic analysis. So what is this thing? So suppose that we start with r to the n with some Euclidean metric. And you can ask, I can ask, what are the transformations of this space that preserve the metric? So, can you think of any?
Rotations?
Rotations is a good thing, yes. Rotation preserves all the lengths of all the vectors. Is there something else? Yes, translations also. They don't fix the origin, but it doesn't matter. This is not a. I see this as a sort of like manifold. You can, not preserve the origin. You just want to preserve the metric. So translations are fine. They preserve lengths of all the vectors. If you have a vector and translate it, it's still the same length. Is that all? Is there anything else?
Identity.
That belongs to both. Is there something that's not the identity translation or rotation and still preserving the metric? Yeah, there is reflections. But yeah, overall there is nothing more. There is just that. But you can ask another question. You can ask, are there any transformations that preserve the metric up to a scale? So what this means is that in particular, it means that you want to preserve the angles, because the way you calculate angles is that you take the fraction, you divide some stuff, and if you scale your metric, then the angles stay the same. So is there any transformations on top of these ones that we mentioned that would preserve angles between things? Yes, you can do scaling. You can do stuff like you move away from the origin, So scaling is an example of a transformation that preserves the metric up to a scale, up to some factor. And so, okay, so this was just a pictorial thing, but let me make it.
Inversions.
Sorry?
Inversions.
Inversions. Well, if this is r to the n, well, if you would have a punctured plane, then maybe.
Yeah.
Punctured. Yeah, that would work, I think. Okay, so definition. So let's make it more general. So suppose that. So let M be it's a Riemannian manifold. So manifold. It has, okay, maybe better say M and G. So you have a manifold with a metric. For instance, this one. And then you say that the transformation of this space into itself, so diffeomorphism, so just a nice map from M to itself. By the way, I should say that one thing I forgot to say is that there is many kind of tools that we will be using in studying conformal field theory. There will be a little bit of geometry, a little bit of algebra, a little bit of complex analysis. And if at any point you feel like that you are not too familiar with one of these things, then I would still not despair, because there will be various sort of half disjoint bits, and if you are lost in one bit, it's still, like for instance, here I will use a little bit geometry, but then I will soon move to algebra, and then if you didn't get the geometric part, you can still follow the algebra hopefully, and things like this. So if at any point you feel a little bit lost, you can, first of all, you can tell me, or you can wait until there is different part which will be understandable. But anyway, okay. So a diffeomorphism, let's say phi, is called a conformal transformation. If it preserves the metric up to a scale. So formally it means that you take the metric, pull it back, and you get some scaling, which means that there is some function lambda for some function lambda x. And in this case, we saw that translations, rotations, and this kind of uniform scaling, they all have this property. So all conformal transformations form a group, which we will call conformal group. Because if one transformation preserves the metric up to a scale and another one as well, then If you compose them, then they will also preserve a metric up to a scale. Conformal transformations form conformal group. But actually, most of the time we will be working infinitesimally. So, which means that we will only be considering very small translations, very small transformations. So, infinitesimally. Okay, so this is kind of the finite, the group version, but instead we will mostly be focusing on infinitesimal things. So we will say that a vector field, say V, is called, so the analogous condition for a vector field is called conformal killing vector field. It's called conformal killing vector field if at the same condition, if it preserves the metric up to a scale. Here I can be more explicit, and instead of writing pullbacks I can tell you in coordinates what this means. It means that if you call the vector, let's say, I call it V, and I will. How did you decide to do? Okay, let me call the coordinates with the components with lower small v. If this is the vector field for some coordinate system, then the condition of conformal killing is simply this one plus v mu equals lambda g mu nu. So you can, yeah, it's not difficult to simply take this condition and take a lead derivative, take the infinitesimal version, and look at it in coordinates, and for some function. Okay, so maybe just to say it in different words. So whenever you have a vector field, a collection of such components, which satisfies this equation, it means that it's a vector field which will if you flow a little bit along that vector field, then you will preserve the metric up to a scale. Okay, is that acceptable? Okay, so now, and just as before, the conformal transformations are assembled into conformal group. So, okay, let me just say conformal killing vector fields. Vector fields form what is called, what I will call conformal Lie algebra. Fields form a conformal Lie algebra. Okay. It means that whenever you have two vectors of such sort, and you take their commutator, it also is preserving the metric up to a scale, so it's also a conformal killing vector field. And together they form a conformal Lie algebra. Now let me be more specific in what this thing actually is in examples that are most important. So, proposition. So take the case we had before, n was just r to the n with Euclidean metric, so constant, the simplest that you can have, metric. And very importantly, you take n to be smaller or larger or equal to 3, so at least 3, 4, 5, etc. Integer. And then the conformal killing algebra, the conformal group, the algebra, the conformal algebra is isomorphic to a group which is quite simple, literally. Big. the special orthogonal Lie algebra. Lie algebra is isomorphic to so n plus 1 comma 1. So it's a finite dimensional non-compact Lie algebra of this specific type. But actually we will be really, really interested in the two-dimensional case. So this is kind of, I'm just writing this for completeness. So the only thing to remember from this is that in this 3 and more dimensions, there is finitely many space of conformal killing vector field is finite dimensional. It's a finite dimensional space. The conformal group is finite dimensional. But in 2 dimensions, something different happens. So is this okay so far? So now, okay, let's focus exclusively on 2 dimensions. We take R2, the coordinates, okay, I call them x0 and x1, because I thought I'm going to use the zeros coordinate, but then maybe 1 and 2 would be more appropriate. Doesn't matter. So the metric here, I will take the same, the Euclidean metric. If you write it in terms of this metric tensor, then it looks like dx0 squared plus dx1 squared. So that's literally the picture there, just R2. Now there is a little trick that you can do in order to, so I will now try to solve this equation in that case. But there is a little trick which you can do, which is to sort of cheat slightly and introduce complex coordinates. So you realize that this thing is secretly the same as C, and there you define a choice of coordinates, a different set of coordinates. So instead of x0 and x1, I will take z and z bar. Okay, this is how I write z. Hopefully that's okay for everyone. This is lowercase z. Okay, so we take this to be just this guy, and this thing we take minus I x1. So I'm doing it, so the way you should think about it for now is that, imagine that instead of I would say like 2 or 3. So I would make like a real change of coordinates. And instead of that, I'm kind of making a slightly different real change of coordinates by putting an I here. But think of it in first approximation as making just a simple change of the basis, and ignore the fact that there is an I in there. Just all the formulas look. You can still work with the formulas if you do it that way. Anyway, it's easy to show that in these new coordinates, G will look as dz, dz bar. And to see that, you just go back. So I just substitute this thing for z. dx0 plus I dx1, and dx0 minus I dx1. Yeah, and then if you multiply them, first with first gives dx0 squared. The mixed terms will cancel because it will have dx0 dx1 with minus I, and you will have it the same thing with an I, but they cancel. And so the only thing that remains is the last thing with the last thing multiplied by I times minus I, which is 1. So that's why you get dx1 squared. Okay, so this is just to show that it's really the same object. But note that in these new coordinates, the metric tensor is so if you would write it as a matrix in here, in these coordinates, you would get this. In these new coordinates, it looks somewhat simpler, but if you write it as a matrix, it really means that it looks like this. So there is no dz, dz bit, 0. dz bar is also 0, and there is only dz, well, this 1/2 is, okay. Okay, so the metric kind of looks simpler when you write it like this. And now we can just go back to this thing. So the advantage of this expression is that this is a formula which is independent of the coordinates. So if you change coordinates, it still looks the same, and it also looks the same if you change your coordinates to this kind of weird complex thing. So you can just take the same equation, and we can just substitute for an indices mu and nu. We can substitute z or z bar. So there will really be three equations. So partial z vz plus partial z vz equals lambda g z bar plus bar vz bar plus okay, so this thing is symmetric in mu and nu, so there's only three equations. Okay, so now I just wrote that thing in our coordinates. Now we can look at what the metric tensor is. So we see that there is no zz and no z bar bit, so these things are 0. This thing is 0, this thing is 0. And okay, so the first equation, because this is twice the same thing, it just tells us that partial z vz is 0. Last equation tells us that partial z bar of vz bar is 0. And this thing is kind of an empty equation because it only tells us that lambda was a function. This thing here is 1/2. So this equation only allows us to express lambda in terms of something. So like it doesn't give any new constraint on v. So this thing determines lambda. But as far as constraints on v, it doesn't give you any constraints. So the only two equations that you have are those two things. Those are the conformal killing equations in the 2D case. But note that the indices, I wrote them down, because that's how they appear in this equation. But you really want this v, they are here. So vector field is an object whose core components have a natural index up. And if you know about Riemann geometry, you know you can move indices up and down using the metric. Because the metric is of this off-diagonal form, this means that this thing is the same thing. Somewhere there is a 1/2. On one of the sides there is a 1/2, let me put it here. So you can erase the index using the metric, right? Because objects with upper indices are defined as objects with lower indices, and vice versa. So, and you have the same thing for the other guy. Again, there is a 1/2, maybe I put it on the wrong side. But the important thing is that these equations, when you write them in terms of components of the vector, then they look like partial z vz bar is 0, and the other one says partial z bar vz 0. So now I will make a simplifying change of, well, I will introduce a different notation. So let me call vz, we call it simply v, and vz bar I will call it v bar. And instead of writing partial z, I will write partial, and instead of partial z bar, I will write partial bar. And with this amazing change of, well, with this amazing notation, the equations just become this, and this. So this trick is called choosing a notation. Also, actually, because the whole thing at the beginning, this was, I didn't say it explicitly, but this was, everything here was real. The first time complex coordinates appeared was somewhere here. And you can show that, you can get one equation from the other by complex conjugation. So really, the only important thing is just this thing, because you can get this one by complex conjugation. Okay, so let's, actually, sorry, I want the other one. One is nicer. Okay, so to summarize all that happened so far, we are studying vector fields which preserve the metric up to a scaling. In dimensions 3 and above, it turns out that there is only a finite dimensional space of these things. In 2 dimensions, it turns out that the equation that determines this behavior is simply this one. This one, the bottom one. V. And V, if you remember, V was a component of some vector field, so this is just a function. So V is a function that a priori depends on our coordinate z and v bar. But the equation to solve tells us that actually it does not depend on z bar. It's a holomorphic function. So, okay, so this is the same as to say that V is a holomorphic function. And each holomorphic function gives us a conformal killing vector field. So conformal killing vector field, there is how many of them there is? There is as many as there are holomorphic functions. And how many holomorphic functions there are? Let's see. Infinitely many, yes. Because we can take V to be Z to the n. That's holomorphic. You can take any n. So in 2 dimensions, it's infinite dimensional. That's the upshot of this. Continue here. So any questions for this part? I guess one takeaway message might be that 2 dimensions are somewhat special. That's one thing that follows from this calculation. Also, secretly, this is okay. It's probably fair to say that this is the same reason that string theory is a theory of one-dimensional objects. That's kind of, roughly speaking, somewhat related to this fact. Because in space-time it cuts out the 2-dimensional surface, and there is something about conformal field theory that's important there, and that's why 2D. And that was very unclear, but maybe we will touch upon that later on. Okay. Yeah?
It's somehow just local, right? Like if you want to understand like global
Very good.
things, like holomorphic bijections from C to C, they're just AZ plus B, right? It's just like
There is not. Yeah, exactly. Yeah, there is some things that I'm not saying. So I passed to the infinitesimal version to vector fields, and if you really want this to integrate them to a group, then that's a different question. So I'm kind of purposefully avoiding that. But at least what you said about local things, that's a thing I forgot to say. That this analysis that we did with this end result, this thing is in particular true if you take M to be any. You can take M to be not just C, but you can take it to be, you take C as the plane, and you take any open subset. You take this thing to be your M. And the same analysis still holds. It's the local, whatever the algebra is still given by holomorphic functions. And in particular, a particular interesting example is when you take the punctured plane, you take C without 0. So let's do that. Let's take the punctured plane. So, okay, let's take M to be C star or something. Punctured plane, when you remove the origin. So in this case, you can take Z to the n for any n, even a negative power, so negative integer powers, because they are still well defined when you remove the origin. You can have 1 over z, 1 over z squared, etc. So let's define a basis. I will call it ln. This thing will be minus, and for some obscure reason I will put 1 here, and then partial with respect to z. So these are some particular vector fields. They are holomorphic, so that this thing is in particular solving our equation over there. And it forms a basis of all the holomorphic things. So all the holomorphic things you can write is like with some maybe a little bit hand wavy as a linear combination of such things. So I will pretend that this is the basis of our conformal Lie algebra. So let's calculate what is the commutator of two such things. Okay, let me use the index I. Maybe. Okay, so taking these basis elements, let us calculate what the algebra actually looks like.
N is an integer.
Oh yes, sorry, thank you. That was important, yes. Yes, thanks. That's why I took the punctured plane. With the origin removed, you can also have negative powers. If it was C, then you would need to have n equal -1, 0, 1, etc.
Sorry, I missed it. X stands for like arbitrary dimensional. C?
No, sorry. This is like a okay.
Ah.
Let me say star. Actually, it's not. What's the proper notation for punctured complex plane? Is it? Okay. Yeah, let me keep crossing. Cross standing for the puncture. Okay, anyway, so let's calculate what this thing is. So how do you do that? So you just take the commutator of vector field. So for instance, imagine that you take a function. So this is some function. And you are acting on it. So this is the same as acting with one operator and then with the other one on f minus the other direction. Okay, let's do this. Okay, this I is not to be confused with the complex unit. Maybe J, A, K would be, okay, let me put K instead of I. Apologies. K and J. Okay. Strange order, but doesn't matter. So, okay, so I apply twice, so this minus goes away, so this, because it appears twice. So this Z to the K plus 1. Partial derivative with respect to z, acting on z, j plus 1, acting on partial derivative on f. That's the first term, and then the other term is just the same thing, but you exchange I and j and k. By this I just mean the same expression with j and k exchanged. Okay, so now the derivative can hit either this guy, in which case I get j plus 1 in front, and what remains is z to the j. So if I multiply them, I get z to the j plus k plus 1, and all of this multiplies partial f, right? So this is what happens when I hit the first guy, and then I can hit the second guy, in which case I take these two things together, j plus k plus 2, and then I will get two partials on f. And all of this, I have to subtract the same thing where I exchange j and k. So it's minus k plus 1 z, and if I exchange them, I still get the same expression, same power. Same here, z. Okay, and we see that these two things cancel. The ones cancel as well here, because the powers are the same. And what remains is j minus k multiplying this guy. Partial f. And now using the definition, you can see that this thing is simply minus L with index j plus k. I will use the minus, I will absorb the minus by swapping these two guys, so I get k minus j L j plus k acting on f. And this holds for any f, so then therefore I can write the result as commutator of Lk and Lj is a number, k minus j, multiplying another basis element, which is Lj plus k. So this is kind of the relevant bit of the conformal Lie algebra in 2 dimensions, and this thing is called Witt algebra. So in notes I put some sort of exercises along the way. So an interesting thing to do at this point is to kind of realize that this thing we did on the punctured plane. So if you do the full complex plane, then you don't get all integers, but n has to be bigger or equal to -1. So you get some sort of truncation of this thing. You get different thing. But a particularly interesting thing. Okay, so it's just an exercise that you can do. You can see how many of these ln's survive when you go to CP1. So you take just kind of the same as a complex plane where you adjoin the infinity. So, well, you see, well, the ones that have negative powers of z, they don't survive. So it has to be, n has to be at least -1. But it also turns out that if n is high enough, then this expression is not well defined with infinity. So you can check which ln survive on CP1. By this I mean which of them are actually well defined. And the way to do that is that you need to switch from z to a new coordinate around infinity. So you define w, which is 1 over z. And if you change your vector field to the w, or if you express it in terms of w instead of z, then you will see that there's a new upper restriction on the range of these guys. And it turns out that only 3 of them survive. And you can calculate the algebra that these things give, and that's one of the exercises if you want to have a look at it. But we will not be using this. This is just like a fun side exercise. Okay, this is all I wanted to say in the first part. So are there any questions for this? Is the general idea clear? Like areas and stuff.
I have a question.
Yeah, please.
Could you give some physical interpretation? Because the only ones I know of are the light cone coordinates. Or if you have some electromagnetic field and stretch that out to the plane when you have, you know, the rotational.
So, examples, you mean like examples of theories where this thing is a symmetry, or?
No, in a physical sense, you know, like in 2 dimensions, which examples you can give in a physical way, you know, like cone coordinates, for example. I'm not really sure I understand the question. Okay.
But in what way do you mean the light cone? Like, how do the light cone coordinates fit in here?
Yeah. I mean, you showed us on the previous record that if you choose the metric to be, you know, two-dimensional with x0 and x1, and one of them has an imaginary part.
Mm-hmm.
And I know this for if you
mean like a
complex time,
Okay.
that you can describe the light cone on a, let's say, on a Penrose.
Right. So this z and z in like this z and z bar in some sense correspond to the light cone coordinates. Like similarly, when you make a change of coordinates in like
Exactly.
dimensional Lorentzian space and you switch to light cone coordinates, and the metric will have the same form as here. Right?
Yes,
It will be
yes.
off diagonal. So that's true. But I'm not sure if I can say anything more interesting about it.
Or could you please draw some examples of field, how it looks like in R2 for Z or Z squared?
Ah, you mean with the vector fields? Oh God. Okay, I should be able to do that. Yes. Right. So let me think. Okay, so there's this puzzling thing about the fact that I passed to the complex coordinates. But anyway, like if you look at the first few guys, then L minus 1 is given simply by partial with a minus maybe. Okay. L0 is minus z times partial. L1 is minus z squared times partial. And that's a fair question. I would rather leave this as a sort of exercise because I did not prepare for this bit, although I should be able to do that. But like, okay, so the thing is that okay, this is kind of the vector field V. So you need to, in order to make it really precise, you should also adjoin the V bar to it. So you really have the full vector field, and then you pass back to the x, y coordinates and x0, x1, and then you should be able to draw some pictures. Sorry, that's all I can say at the moment. But it should not be hard. Yeah. But in particular, you should from these things you should recover translate like. Yeah, you should recover translations, translations, savings, and special control. Okay. Okay, I will rather leave it for later. I can have a look if you want, but that was a fair question. Any other questions that I won't be able to answer? There's another question. Okay, let me return to this, and at least what I can say is that so these things form a complex basis of. Okay, so you should be able to multiply this with any complex number. So we can say like linear 1. So if I take complex linear combinations, then out of this I can get del, or I can get just secretly just partial z. Okay. Okay, now let me rather skip then look at it later on. But you should really combine it with the V bar, put it together, and then look at what it gives you. Okay. Now let's go for a completely different topic. Yes?
So, small question. So we can, since that was the local picture, so we can do it for any Riemann surface.
Yes, as far as the algebra goes, yes. Yes, yes, you need to study holomorphic vector fields on the Riemann surface. Yes?
I think that's not the like there are three more independent generators, right? For the two-dimensional case. For the conformal group, there are three more independent generators, right?
You mean in 2D?
Yeah.
Because it's 6-dimensional.
Yeah.
Yeah, but yes, but you can take, you know, complex linear combinations of these things. So that's 6 zero parameters. Okay, good. Thanks. Okay, let me now for a moment completely switch gears and let me talk about QFT and CFT. So I want to give some sort of feeling, mostly to the mathematical part of the audience, to what kind of a thing you could imagine behind QFT. So it will be a bit restricted, but well, I think it captures the picture. So okay, so let me. So this bit will be a little bit heuristic, but then we will get back to like a more precise algebraic representation theory and a little bit of geometry and complex analysis. But so far, let me just tell you the motivation, where this comes from in physics, etc. So in this first bit, let me describe what I will call a Euclidean QFT, a quantum field theory. As I said, this thing is kind of at the border between math and physics in some way, so let me at least give you some sort of heuristic definition of such a thing. So what are the ingredients for such a thing? What is the data? What should I think about when I get such a thing? This might be partly subjective, so this is kind of the stuff that I picked up to be representative of a QFT, but you can maybe pick up something better. But anyway, let me, as one part of the data is a space-time. So think of a manifold, Riemannian manifold as before. Most conveniently, just take this one with the Euclidean. In principle, we can do more general, maybe not. But this thing works. Okay. More importantly, there is a Hilbert space, so there is a complex Hilbert space. Which contains a distinguished state with a vector with a distinguished vector, which I will call vacuum. So this notation is just a notation. So you can just, instead of this, I could just say V, but I will adhere to the usual physics notation and I will use this so-called bracket thing. But if you wish, you can just write V instead of... This whole thing is just the name of a vector. Okay. That's the vacuum state. Okay, the third bit is a collection of fields. So fields, but by this I mean, okay, let me write it, some chosen class of linear operators I will index them by some index alpha, and they will be depending on the position. So that's why we call them fields, because it's like electromagnetic field. They depend on the position. So X. Okay, so they depending on X, and such that they satisfy the so-called locality. Which here is just a simple condition which says that whenever I have two such operators, say O alpha and O beta, and I put them at different points, then they commute. I'm sorry. Alpha X. If X is different. So here, maybe a remark for physicists. So maybe you've seen, maybe not, but in normal quantum field theory, which is not Euclidean but Lorentzian, you usually want this thing to hold whenever the insertion, the parameters are space-like separated. But in this simplified Euclidean setup, the analog of space-like separated is actually like all points are space-like separated unless they coincide. So that's why they actually commute for all things. So it's just a remark. That's why this condition arises. But you can just take it as a condition. So that's one. And then also I want that the set O alpha includes the identity operator. And there's a fourth bullet point, the last one, because actually what I wanted to define is Euclidean quantum field theory with symmetry group G. The last ingredient is a representation of the group G, and what I want specifically is a so-called projective representation. Of G on H, by which I mean, okay, i.e., this is just a homomorphism from G. So if this would be a normal representation, then I would want to represent this in terms of some invertible operators on the on our Hilbert space. I will just call it GL. Maybe it's a bad notation, but I mean, if this would be finite dimensional, then GL would be the correct notation, so I will just keep it. So invertible linear operators here. Projective representation means that I'm not doing this, but I'm actually representing this on this okay. Remark. So these things sit inside GLH by simply taking a number A and I map it to A times identity. And that's a normal subgroup I can divide. It's actually a center of the thing, so I can divide by it, and I get a zero. And projective representation just means that I have a homomorphism like this. And again, a remark for physicists. So normally you don't see this word projective. So the reason I'm adding it is that the really relevant objects in the Hilbert space are not the vectors in here, but are the rays in there, because states are defined up to a phase, so you really care about one-dimensional subspaces of that guy, and that's why you want to represent you don't really care about the scale. So the proper thing that in some sense you want is a projective representation, but, and I will get to it in a moment, we will trade this off for a normal representation of a slightly modified group. This is just to say that projective is there because we care about the states. The physical states are not vectors in here, but are one-dimensional subspaces. That's the reason why they write it. Okay, that's end of the remark for physicists of how this connects to the usual lore. And just to finish this, so I will impose to make it complete. I want that this group preserving vacuum state, or the one-dimensional space spanned by the vacuum vector. So I want the vacuum is preserved by the symmetry. And also it's a good practice, let me put it as in parentheses, that G should contain a group of isometries of H, of M. Group of isometries of M and G. Okay, so that's sort of like a slightly hand-wavy, but hopefully illustrative enough definition of what a quantum field theory is, yes?
Sorry, probably not too relevant here, but what's the meaning of a distinguished vacuum?
I just mean that there is one vector that you call vacuum.
Ah, okay.
Yeah, that's just I want a space and a concrete vector in it, which is non-zero.
Thank you.
Yeah. Actually, the thing with vacuum I could have just as well ignored. I just decided to include it for more physics words. Okay, does this? I know that this is not I didn't tell you what kind of class of operators I take and everything, but this is like kind of the general picture of what is happening. So physicists have some means of constructing such things by starting from what is called classical field theory. So if you start with the classical field theory, then often you can do some magic and squint your eyes and pretend something works, and then you get something like this. There is also theories which in principle do not need to come. There is setups of this type which do not necessarily need to come from classical field theories. They actually very often arise in conformal field theory. But anyway, so this is kind of the picture to have in mind.
Are there, like, is there a general list of axioms that this class of operators needs to satisfy?
So for us, it will be just this.
Just this, okay. So can I just take one operator, which is the identity? It would satisfy?
Sure.
Okay. And that would be a CFT?
No, this is not QFT so far. I mean,
Okay,
these things, there is more conditions that you typically want this stuff to satisfy, and this is kind of just like, these are the ingredients that happen, and there is maybe some more stuff, but...
That's what I'm asking, like, is there an agreed upon list
there is
of
this thing
axioms?
called Whitehead's axioms, which I kind of partly reproduced here to some extent, that they are like an attempt to axiomatize QFT, and they say that you have like fields are distribution valued operators on something locality condition, and then something, and but they are, but those things, they can get you somewhere, but it's not clear, for instance, how to formulate the famous like Yang-Mills and things like properly in terms of these axiomatic frameworks. So this is more like an idea. Not very concrete, because I didn't tell you what class of operators and everything, but just some idea.
What's the link between G, the group, and the fields? Is there like an axiom link?
Well, yeah, there should be something, yes. Yeah, they probably, you want them to transform in some representations of G, or that's a meaningful thing to add, yeah. Okay, so this plus maybe some other stuff. We started half past? Okay. Okay. Going pretty fast. Actually, no. Well. Okay, so what do you usually? Okay, so let's accept this as sort of like a very bad definition of a QFT. What are the things that you typically calculate with it? So what do we want from this? Or like, no, what do we want to do? Let's say to do with this. By the way, one thing that I didn't say, maybe I should have, is kind of to give some more connection to real world, real life. So this G typically wanted to include the isometries of the group, and in particular, if the, sorry, of the space. And if the space was just Euclidean space, and let's okay, it's Euclidean. But imagine that if I would do something similar for Lorentzian. So I would pick a metric which would not be positive definite, but it would have like one time direction. Then in particular, the group of isometries should include translations along the time direction. And that's how in principle you describe the evolution of states. So you have a state, which is a vector, or better, array, one-dimensional subspace in here. And you can describe its evolution by simply applying this operator representing the time translation. Okay, so you have time translation, it's part of G. G is represented in here, so it gives you an operator, and you can apply that operator to the state, it evolves. And that's what you typically want to calculate in principle. Okay. I confuse further people, but good. Okay, so what do we want to do with this? And this is kind of the end baby part. So typically what you want to calculate with such a thing is correlators. By which I mean these are expressions of the type. Okay, let me maybe alpha 1 x1. these are objects that you denote like this. The definition of that is that you take your vacuum vector and then you apply all these chain of operators. So O1, O alpha 1, at point x1, O alpha n, n. Okay, here I assume that that xi is different from xj. If I is different from this, so I don't want them to coincide. I wanted them to be all inserted, all having, all being sitting at different points. So I don't want any of the two insertions to coincide. So if I do that, then it doesn't matter in which order I put the operators here by this axiom. So this, I have a state, I have a vector in the Hilbert space. I apply a bunch of operators, I get a new vector, and then I take a scalar, an inner product with the vacuum, which is denoted like this. Okay, so this is, so physicists probably know this very well, but like maybe just for mathematicians, this is called the bracket notation. So if you have two vectors in a Hilbert space, and let's call them something like rho and sigma, they are typically denoted by, okay, this might look automatic for physicists, but let me just spend a minute on this. So this is how you denote, in bracket notation, how you denote vectors. You just put them in this silly thing, which is called a ket. And whenever you have an inner product, okay, let me continue here. Inner product of rho and sigma, but let's maybe apply some operator on it. So this is a vector and this is another vector. So this is denoted this is called bracket notation. This guy is called a bra. This is called ket. If I remember correctly from my physics days, this was introduced by Dirac. Is that right? So yeah, this is just a dictionary. Whenever you see this in some physics papers, then it's, you can just as well write it like differently, but it's sometimes good. Yes.
So ket is a vector and bra is a string.
No, bra is a covector. It's a covector.
Yeah, covector. So I can think about it as a string.
What do you mean by strings?
Well, row. Yeah, we have columns and rows. Yes. So vector is.
If you want to, yeah, then yes, in that sense, yes.
Yeah.
But abstractly, it's an element of a dual vector space.
Yeah.
So abstractly, if you have this thing in a Hilbert space, and whenever you see expression like the opposite, then this just means this is the covector obtained by taking inner product with the vector. With the vector law. Representation theorem or something. Right?
Used representation.
Yeah, thank you. I see people are confused. You seem confused.
No.
Okay.
For once.
Okay, this was not terribly important, just wanted to, since I'm pretending to give some sort of dictionary, then why not mention this? Okay, so this is an object that you try to calculate in QFT, and from this, if you are clever, you can obtain some measurable results, some particle collisions and things. For us, I wanted to mention one thing, that like one way to calculate these things that's sometimes used, and it's particularly important in CFT, is that sometimes it's useful to calculate these things using so-called a thing which is called OPE, operator product expansion. This is the following thing. So it is often the case that if you take two operators and you insert them at some 2 points, which are different, and when you are trying to approach with, if you take your x and you are trying to approach y, and if you get close enough, then sometimes you can expand this in terms of some other operators, which are sitting at y, and there is a bunch of coefficient functions in front, I guess, which depend on x and y, and if you're lucky, then these things happen to be sort of nice functions that you can use. And whenever you see such a thing, you can call it an OPE, that you expand the product of operators in terms of other operators. And the way you use it is that if you have, like, let's say 4 things in here, then you can try to take some pairs of them, expand them, and by this way you effectively remove one operator for the price of having an infinite sum, etc. But you can lower the number of things until you get like a correlator with one field only, and that's easy to calculate. It's usually 0 or 1. So, okay, this is the end of the hand wavy part. Yes?
Should it be like inside a correlator? If I remember correctly, that the OPA works only inside correlator.
Yes, that's a very good point. That's a very good remark. I was trying to avoid that. Yeah, I mean, it's okay. So when I first encountered this, I also saw it like that. So people they say that you write such equalities whenever they hold inside correlators, which means that if I would put other insertions, other operators, and I would put correlators around them, then it's the same. I was kind of hoping that in some cases this might hold literally as in terms of operators. Okay, in the worst case scenario, this is inside correlators, I agree. But at least for, okay, let's pretend that this holds actually on the level of operators as well, not just correlators. Yes?
I was wondering, connected to this axiom discussion, is it like required for this set of operators such that this OP is usually closed? So if you take the product, you again land in the set of operators?
That's a very good thing. Very good question. I was kind of very vague and incomplete in this, but in order for this all to make sense, that seems to be the assumption that you would need to take. Yes, that probably I should have put in here. That if you, that's probably a good idea to actually include this as an axiom that it actually closes under the. Yeah. Yeah, I was sorry. I mean, there is lots of stuff hidden behind this, and of course the situation is not as easy as I was sketching here, but yeah, that would be a reasonable thing to add. Thanks. Yeah, apologies for the sketchiness of this section. Okay. Okay, then. Okay, with this, then I can comment on this one little bit that no one asked me about, but it's kind of the important for me, and that's this projective representations. So. So, as part of the definition here is that you want to have a group which is represented in this way. But optimally you would like to have a normal representation, which means that you would like to have a map GLH. So you can ask, like, is it possible to, if you have a general homomorphism of this type, is it possible to actually construct another homomorphism like this, which will give rise to this one if I project it to this quotient? And the answer, unfortunately, is no. In general, I cannot do that. It's not possible that it's not possible to lift a projective representation to a linear representation. Such a thing I would call linear representation, or ordinary or normal or whatever representation. But it can be shown. It's actually quite easy to show that you can always trade off such a thing for such a thing if you, instead of G, if you take a slightly enlarged group G. So this thing is what is called a central extension of G. It's not difficult to say what this means, but let me just be vague for now, and let me just say that it's another group which is only slightly different from G.
I haven't undefined it, so it's.
Oh, you did?
Yeah.
Okay, I unfortunately missed his. Okay, for groups.
Yeah.
Did he also talk about projective representations? Okay. There's that. Yeah. Okay, so I wanted to say a couple of remarks about this. So again, first remark is intended for physicists. So you know that in the theory of spin, what you start with is that you are looking at the group of rotations of three-dimensional space, and you are trying to see how you can represent this on the Hilbert space, on the states of your system. So for instance, you have an electron, which is like two-dimensional representation. But what you are secretly doing there is that you are studying projective representations, because those are the ones that you really care about. Projective representation of SO3. But in fact, when you look at what people do in textbooks, then you don't do really this, but instead what you trade this off for a normal representation, a linear representation of SU2, which is famously the double cover of SO3. So something that's slightly larger than SO3. It's like twice as large if you want. And indeed that fits into this framework because because this thing is a universal cover of SO3, and universal covers of groups, they are particular cases of central extensions. So this is what's happening in the background when you study spin. Originally you were interested in this group, but then you end up with this group, but that's because you really want to study linear representations. Does this make sense? Okay, so this was a remark mainly for physicists. So for everyone, so we are interested in conformal field theory, so I actually didn't give it a definition. So definition is that conformal field theory, CFT, is, now I use those words, is a quantum field theory with symmetry group QFT with G containing the conformal group. Okay. So that's how it fits. You want that group not only contains isometries, but in fact it's bigger and it contains the whole conformal group. And this remark about central extensions, this is just to say that if you are in dimensions higher than this, 3 or more, then it turns out that the conformal group, G, which is the conformal group Rn, with Euclidean metric. So the group that you see, that you're looking for, this G hat, it turns out to be the same as G. And the fact in the background, which is kind of the reason for this, is that the G has vanishing second cohomology. Has vanishing, or let me do the Lie algebra. Vanishing second cohomology. The group, if you remember, this was SO n plus 1. And you can show that that thing has a vanishing second cohomology, which means that it has no non-trivial central extensions, and this means in turn that every projective representation of this group can be lifted to a linear representation of the same group. So if you go to 3 and higher dimensions, then in this definition I can just omit this word projective. But in 2 dimensions, famously, this G, or let me work with Lie algebra. So we had the Witt algebra. And in 2D, it turns out, that's an interesting calculation, that you can show that there is a one-dimensional second cohomology, and it means that there is it implies that there is a unique central extension that you can make. And it turns out that in this case, the hatted object is what is called the Virasoro-Lie algebra. Which I'll Vir stands for Virasoro. In case that's not clear. One dimension is not interesting enough, so I will skip that. So the moral of the story is that in studying 3 and higher dimensional CFTs, you don't really, you can forget about all these subtleties about projective representations. In 2D, it turns out that you can, that what you really want is to have either projective representations of this guy, or you want to have ordinary representations of this guy. And that's why this Virasoro algebra, which I will now define, is kind of the central object in CFT. This was a very, very roundabout way of getting there, but hopefully you can get something out of it. So, Virasoro algebra. The algebra generated by I will call them, I will use capital Ln. N is now n integer. And another vector which I will call C hat. Okay, so these form a basis. So basis is Ln for all integers and this C hat. And the commutation relations are such that Ln and C hat commute. Well, C hat obviously commutes with itself. But more importantly, if you take a commutator of Ln and Lm, this thing starts the same as in the bit algebra. But there is another bit. So this 12 is just purely not for convenience. It's not important. And there is another term that appears here. It's proportional to the vector C hat. And it only appears whenever, this is the Kronecker delta, so it only appears when n plus m are equal to 0, when they are opposite to each other. And this is a fun little calculation, but you can show that this is the only trivial central extension that appears. I guess this is okay. Any questions? And then I will make a break. Yes.
I'm sorry. By what sense? What does vector mean? Is a vector in Hilbert space or?
Say it again.
What does the vector C vector mean? Is it a vector in Hilbert space or?
This is not a Hilbert space. This is like a separate Lie algebra that acts on the Hilbert space. So you just imagine that you have an abstract vector space, and the basis of that vector space is given by these things, infinitely many of them, and then there is another guy, which I call C hat.
Okay.
It's just basis vectors.
Yes.
So the basis of Virasoro is Ln and from minus infinity to infinity, and on top of that another vector. Any other questions? Okay, if not, then let's make a break. Let me say a few words about examples. So, of CFTs. So, what are the theories that have this conformal symmetry? So there is essentially, so very famously, okay, let me just say this in words. So in statistical physics, when people study statistical models, then it happens that near their critical points, like critical temperatures, etc., the systems exhibit some sort of scaling symmetry, and it turns out that those things are very well described in terms of CFTs. There is also another thing, so that's like, and one of the main successes of CFTs was actually elucidating some things in statistical models. I instead want to focus on something that I find a little bit more geometric, and that comes from string theory ultimately. So let's suppose that we have the following thing. So suppose we start with a classical field theory. It's just a fancy word which means that I will have some space, let's say r to the n, and I will study a couple of functions there. So I will take some phi I to be functions in this space. So I will have a collection of functions. If you want, you can include other stuff. You can replace this by a general manifold. You can put a manifold here. You can, apart from functions, you can put some differential forms or tensors or whatever you like. So it's just some geometric objects. So you have a collection of such things. And in order for me to make a classical field theory, you also need an action functional. So you want to have a function that if you give me concrete functions, then I want to have a prescription of how to produce a number. So I need an action functional. I think this was probably mentioned here before. Such things arise in physics, that you have fields and you have some action functionals for them. And it happens sometimes that you can have a setup in which, suppose that we have a particular theory which depends on two types of fields. So instead of this phi I, they will be really, okay, they will be a metric. So I will include metric as one of the fields. And then there will be a couple of other fields, which I can call, I don't know, chi I or something. So suppose we have a theory which depends on a metric and on some other field, chi. And suppose furthermore that this thing is invariant under two things, under diffeomorphisms. So if I have a diffeomorphism phi, then I can take my metric and my chi fields, and I can replace them by their pullbacks. So I can use the diffeomorphism to act on these things. And I want that this thing is invariant under such things. So this is a common thing in physics, that you want to have diffeomorphism invariant theories. But on top of that, let's suppose that this is also invariant under the so-called Weil transformations. Which are defined as follows. So you take your G and some other collection, and you just multiply this thing by some function. Okay, where lambda is a function. So this was the same thing that we had when we studied the conformal group. Okay, I will give you examples of such things. There's two very interesting classes of examples. But before that, let me make the claim. So the claim is that now you can, so supposing this, you can construct a new theory. Claim. The new theory obtained by fixing the metric to some value which I will call G hat. So I will obtain a new theory, I will call it S hat, which only depends on the chi's, and I will simply define this to be, the action functional to be simply the original one where I substitute this fixed metric. Okay, so this is what it means. I just fixed one field. I obtain a new theory. And the claim is that this new theory is conformally invariant. And hence gives an example of a classically conformally invariant theory. So, okay, is the statement clear? I will give you a proof now, maybe that's a proof. So suppose that we have, so what does it mean that it's conformally invariant? It means that whenever I take a function, call it, if I take a diffeomorphism, if I have a conformal transformation phi for this fixed metric. So by this I just mean that if you pull back this fixed metric, it gets multiplied by some function, let's say omega G hat. So if I have a conformal transformation, then I can now look at what this conformal transformation phi what does it do to my new theory? Like, how does it, if I act with it on these fields chi, what does this thing give me? Is it the same that, is this thing the same as S of chi? And the claim is that yes, it is indeed the same thing. And to show that, you just write the following. So you just, okay, what is this thing? It's defined by using this fixed metric in the original action functional. Now I will write a new equality. Why is this true? Why is this thing the same as this other thing? What property did I use? So, what is this thing? By definition, I require phi to act like this. So this whole thing, I can just substitute e to the omega v hat. And then why is that thing the same as this thing? Yes, because it's invariant under the Weil transformation. It's invariant under this. So here I used Weil. But what can I do now? I can now use the second, the diffeomorphism invariance. So I can just do the same thing as this guy. So diffeomorphism invariance means that this thing and this thing gives the same thing in the action functional S. But now I can go back and I can use the definition, and this is the same as S head of chi. So you see indeed that this thing is invariant under conformal transformations. Okay, so this is a way how you can get conformal, how you can get classical field theories which are conformal invariant. You start with something larger that includes the metric as a field, and you require that it's invariant under these two things. It's kind of a heavy condition, but there is examples. And then by fixing the metric, you obtain a new theory which is conformal invariant.
You just need to fix the conformal class of the metric, is that right? Not an actual metric.
Yeah, that's true. Yeah, I could just as well. Yeah, because of the Weil invariance, it doesn't matter if I do this or if I multiply it by. Yeah, that's true. Okay, so now when does this arise? Like, what are the examples? So note that by doing this, what I obtain in the end is I obtain a classical field theory which is invariant under conformal group. While what I really want is I want to have this obscure QFT, and in order to create that, I need to use some procedure to pass from the classical to the quantum. And there is some standard procedures how to do that, but they might break the symmetries. So it not always goes well when you quantize such a theory. But in principle, at least on the classical level, this is how I can get potential candidates for good CFTs. So example 1. So suppose that, so did I say M? Okay, so let's take M, a manifold, and take N with, let's say, capital G. This is a Riemannian manifold. Now let's call dimension of this let's say capital D. Okay, so I have these two pieces of data, and I can now construct a theory which will be depending on G and X. And this G, I will take this to be a metric on M. And this thing, I will take it to be map from M to N. Okay, so it's roughly fits into that framework. So I have a theory which lives on M, and the fields are a metric on M, just as we had there. The metric was included. And we have a couple of functions. So if you pick some coordinate chart on N, then function to N is essentially a bunch of scalar functions, right? If you pick a concrete coordinate chart, if you imagine this is R to the N, then the map from M to the R to the N is the same as N functions. So that's not a big generalization. I'm just passing from functions to maps to some manifold. If you wish, you can imagine this is R to the N. Even R. So these are the fields. These are our chi and g. And now I need to define the action function now. And okay, and I can only use this data, so let me do the following thing. So I take the metric on, okay, so remember x was a map from m to n. So I take the metric, which lived here on n, I pull it back to m, I get a tensor that has some indices. I can contract these indices with the thing I have already here, which is the metric g. These together create a function, and then I can integrate it. So I will call it omega g, so this is the metric volume form. If you prefer coordinate description, then I can be more explicit, and I can say that this is integral over m. You can take, how does it go? So it's determinant of g, square root of that, g, upper indices, d mu x a, d mu x b, d a b x, and then d, I need to call the coordinates somehow. Okay, let's say coordinates. I guess y. Let's say y. So measure. Okay, so I just wrote fully what it means to be a pullback. This thing is called a Polyakov action. It has the property that it's diffeomorphism invariant, so that's the first condition that we wanted. That's just a consequence of the fact that I use differential geometry consistently in writing stuff. So diffeomorphism invariant is kind of for free. But now the claim is that if this dimension d is right, then this thing is also Weil invariant. So, okay, let me put it as an exercise. Show that S is Weil invariant if and only if dimension is 2. And in that crucial dimension, this is the starting point for study of string theory. So this is what you start with, this is what you quantize, and then you get all the string machinery going.
Once again, X is just any smooth map?
Yes, from M to N.
It doesn't know anything about metrics?
No. These are two independent geometric objects, like a map from there to there and a metric on the source space. And by this general nonsense that we derived above, if we now fix the metric and we obtain a new theory which only depends on X, then the theory we get is conformal invariant. Does anyone know another classical field theory which does have this property that it's Weil invariant and diffeomorphism invariant?
Lewis theory?
Sorry?
Lewis theory?
Lewis? Yes, that would also work. Wait. Can you obtain it by? Yeah, probably as well. I mean, it is definitely a CFD, but I'm wondering whether you can obtain it by fixing the metric? Probably. Yeah, I forgot. But the theory I have in mind is Young-Mills. Just a remark. So it's kind of like a half example. Example 2. If you take so-called Young-Mills theory, Young-Mills theory is also in some dimension, in a concrete dimension, it is conformal invariant on the classical level. So if you take Young-Mills theory, which is the theory where the fields, well, okay. What I mean is that you take Young-Mills theory and you also treat the metric as part of the field. So you have like, this thing is a metric on M, and this is a connection. So let's say in the first approximation, this is a one form on M with values in the Lie algebra of some group. So in some Lie algebra of some group. And you maybe saw this theory, so this, if you want to write it down, this is like, you take the curvature of this, and you take a trace or a pairing or something, and but secretly, yeah, times some volume form. You can also write it as and it's not difficult to see that this thing is always diffeomorphism invariant if you include metric as a field. If you act diffeomorphism, if diffeomorphisms act both on G and A, then this is fine. But it's also while invariant in the equal form. But anyway, this is, well, I say this is a half example because actually when you quantize this, and this is no longer true. So this doesn't give rise to a CFT. If you want to correct that and to get a CFT, you would need to add some supersymmetry to get like super Young-Mills n equal 4 or something, and then that's conformal. But this theory ceases to be conformal after quantization. But this other thing, this is the Polya collection. That one you can make conformal. So. I didn't describe how to pass from classical to quantum, but anyway, if you believe me that there is methods of doing that, then this thing in particular can lead to some conformal invariant theories. Okay.
Sorry, I can read the one form on M
With values in the Lie algebra.
Okay, thank you.
Okay, this concludes the most hand-wavy part of what I had prepared. So. Hopefully it was possible to get something out of it. So any questions or?
You said that. Well, you said that you cannot quantize it.
No, you can quantize it, but it's no longer conformal invariant.
Okay.
Yeah. I didn't describe how to quantize things, so I won't say more about it. But stuff can break along that route. And in that case it does, and in this case it doesn't. But you can quantize that one. It's just it's not conformal.
Can I ask, like, when you're talking about quantization, do you have in mind geometric quantization, or?
Well, I had in mind canonical quantization, or DRC quantization, or any of the other ones, which you can presume. I don't know. You should be. Well, I mean, this is an infinite dimensional setup, so it's hard.
By Young-Mills, do you exclude n equal to 1?
You mean for
electric field?
You mean like U1 or?
U1, yeah.
Yeah, U1 also works for this.
Okay.
Anyway, this was more like for fun. It's not really. It doesn't give rise to CFT. This one does. So in particular, in the most relevant case, or the easiest one, you can take a special case when you take n to be Rn, Rn, and G, not G, sorry, but the big G you take to be the Euclidean metric. And in that case, this thing is just constant. This is 1. This is, sorry, no, big G. This is just constant. And if you fix your G hat to be just, okay, let's be completely simple. Let's just take this to be R2. And let's take the fixed metric to be Euclidean as well. Then if you take these two things, then the fixed theory you get in the end will just be a collection of free bosons. So this is just, all of these things simplifies. This thing just becomes constant. This is 1, this is constant, this is constant. So the whole thing you can write down as d mu xi, d mu xi, sum over I. So it really becomes a sum of independent free theories, and these things are all free bosons. So this is a collection of d free bosons. That's sort of the simplest example of a CFT, an interesting CFT. And we will return to that later on in the quantum setup. We will show how to calculate with such things, what are the OPEs, and how is the Virasoro represented in this case. So this will be our main example later on. Okay, any further questions before I switch to an algebraic part? Okay. So we said that, okay, so let's call this Virasoro representations of Virasoro. I see that I erased Virasoro, but if you remember, this thing was spanned by this elements. So basis is given by this Ln, where n was an integer, and there was one extra guy, which I called C hat. And the only non-trivial commutation relation was this bizarre that when you want to build a quantum field theory with this symmetry, so conformal field theory, then you want to have a representation of this thing on your Hilbert space. So you're interested in, so you really want to study representations of this. So you want that this Virasoro is represented on the Hilbert space. So there's a homomorphism from Virasoro to the invertible operators on your space. And so if everything goes well, you want really to see this as like the sum of some irreducible representations. And so a question that you can ask is like, what are those irreducible representations? What is the possible way to represent this Lie algebra by operators on a vector space?
Here in Virasoro goes not to GL but endomorphisms.
Oh yeah, thank you, sorry. Yeah, because this is a Lie algebra. For groups it would go to GL, so let me that's an important point. Okay, so in order to do that, I will define a order to construct such representations, we will choose two numbers. So let's take H and C, real numbers, or complex, but real will be enough for us. Now, what I will for a Verma module, I will define a representation which depends on these two things. So this is a vector space. Which is generated by the vector space which has the following basis. Like this. More abstract way to write this thing, but let me be more concrete, and let's just say that I will take a vector space which is generated by the kind of formal objects of this type. So I have this object which I will call the vacuum, something analogous to the vacuum, and I will have a couple of things which look like these L's. You can take it as a formal expression if you want at this stage. And I want that this thing will be I want them to be ordered. For instance, it can be any for instance, some of my basis, one basis element will be this guy, another basis element might be something like this guy, etc. So, okay, I have a vector space, and now I need to tell you how to act. How does Virasoro act on that? So, how do I? So, part of the definition, I need to tell you what is the representation structure. So, if I have an LM acting on such a thing, how does it act? What does it do? And so representation, the action of Virasoro is determined by the following conditions. Determined by the following. So first of all, I want that if I act on the vacuum, with anything that's positive, with L with positive label, I want that this is 0. I want that if I act with L0 on this, then this is an eigenvector, so I get back the same thing multiplied by our chosen number H. And finally, to finish the action on the vacuum, I need to tell you how does the C hat act. And the C hat acts by multiplying by C. Okay? Note that here this thing is the number, while this thing was this abstract generator of the Virasoro algebra. And so if I say this, then we know how Virasoro acts on this 0 guy, but how does it act on other stuff? So in general, to determine the action in general, we will use the commutational relations. So call them, we'll use this thing. Okay, so that's, for instance, okay, so that's the, it's a slightly sketchy and not definition, but anyway, the real meaning of what I meant here is that suppose that I have something like a vector L minus 1, L minus 2, 0. So this is an element of my representation, so this thing lives in BHC. And now I want to know how, for instance, L2 acts on this. What is the action of or even better, let's start with L minus 2. So how does L minus 2 act on this guy? And the claim, and that's what I meant by this sentence here, is in order to determine what is happening, you need to use the commutation relations. So you need to kind of massage this thing in a form which looks like this, and then you will get your result. So for instance, in this case, if I start with this vector and I act on it with this guy in the restaurant, then in order to put it in a form like this, I need to have these things ordered. So I need to move L minus 2 past L minus 1 to have it acting here. Like I want to commute them. So I use the commutation relations, which in particular tell me that L minus 1, L minus 2, commutator with L minus 1. If I plug it in, I get minus 3, no, sorry, minus 1, L minus 3, anything that it contributes, so it's the first term. So I use that. So I write. So what I'm doing is that I'm kind of I'm looking at this bit separately, and I write this thing as the opposite direction plus the commutator. And for the commutator, I substitute this value. Okay, so plugging this in, I get the first term, which is L minus 1, L minus 2, L squared, so L minus 2.
Wasn't it already of this type?
Sorry?
Wasn't it of this type at the beginning?
No, because I want to have, I want
yeah, I see.
So I get this guy, that's from the first term, and from the second one, if I set, this is minus L minus 3, L minus 2, 1, 0. Okay, unfortunately this one I still have to massage further, so okay, let me say continue here. Is L minus 2, L minus 2, and 0. And then I need to commute these two things to have them ordered. So I need to calculate the commutator of L minus 3 and L minus 2. And by plugging it in here, you will get that this is minus L minus 5. Minus 3 minus minus 2 is 1, and this is L minus 5. So putting that in here, I will get 2L minus 3, 0, plus the commutator, so plus L minus 5 on the right. And so all these three guys now have the form of these basis elements. And so I see that if I take this guy here and I act on it with this generator, I get a linear combination of three basis elements, and they look like this. And if you want to try, well, one fun game would be to do the same thing, but with plus 2. In that case, in calculating what happens, you would also need to use this central extension term. It's relatively involved calculation in general, if you want to see how things work. And okay, so the thing I did here was like a very explicit type of construction where I really told you algorithmically what to do. There are more abstract ways to characterize this if you want representation theory, but okay, I will just keep this one. Okay, maybe some words. So this element C, this is called a conformal central charge. This guy here, this is called a primary state, or highest weight state or lowest weight state, depending on which sign conventions you use. The other guys, the basis elements with k bigger than 0. So if k is equal to 0, we get the primary state, and the other ones are two descendant states. Descendants. What else? Eigenvalues of L0 are called conformal dimensions. So for instance, this primary state has conformal dimension H. So that's a little bit of nomenclature and safety. So you see that this is a very large representation space. It's infinite dimensional, because I can take k to be as large as I want. Now, is there some good way how to organize that thing? The good way to organize that thing is in terms of eigenvalues of L0. So let's say position, an easy one. The action of Ln increases or decreases depending on the sign, decreases the conformal dimension by minus n. What does this mean? So suppose that we have a vector in our Verma module, V. Let's call it, I don't know, V, the Verma module, such that it has some conformal dimension. So if we hit it with our L0, then we get some number. Alpha. Now, what happens if I act with Ln on my state V? The claim is that I get a new state whose conformal dimension is moved by n, minus n. So how do I check that? How do I check conformal dimension? By calculating what is the action of L0. The eigenvalue of L0. So let's see what this is. So this is L0 Ln on V. Here I can use the commutation relations. So here I use the fact that if I take L0 Ln, then by our formula over there, we get minus n Ln. 0 minus the second argument, and then the sum. 0 plus n is n. Okay, so I can, okay, so what does this mean is I can trade this off, I can solve them, but I will get a second term where I get the commutator, and the commutator will be minus n. Ln acting on V. But now I can use the fact that this guy here, I make a parenthesis here, this thing is the same as alpha times V. That's what we suppose. And alpha is a number, so I can take it out. And I get alpha minus n ln acting on. So looking at it back, it means that if I take this guy, this thing, and I act with L0 on it, I get itself multiplied by a number, which is alpha minus n. It's precisely the statement of the theorem, that I decrease or increase the dimension by minus n. Maybe increase is better, shifts is a more neutral word. Shifts the conformal dimension by a minus n. Okay, so this is just So, in other words, if you look at conformal dimensions inside this normal module, then you can move up and down using the L's. If you use L's with negative arguments, you move up in conformal dimension. If you take these guys with positive n, then you go down. So, okay, so this thing suggests that okay, so picture to have in mind is the following kind of pyramid. So the picture of V, H, C is the following one. So you have at the top you have sitting the vacuum, or the vector, the primary state, which has conformal dimension 0, H, sorry. And then we know that if you act on this guy with L minus 1, then you create a new guy. So this is our basis element that you get here. If you take K to be equal, if you take 1L, so you can create this new state, and we know by this proposition that this moves the conformal dimension by 1. So this is conformal dimension H plus 1. Similarly, you can create a what kind of states of conformal dimension H plus 2 can we get? And how do they look like?
L minus 2 and L minus 1 and
Right, so we have two, thank you, so we have two things. We can either take these or this. Both of them have weight, conformal weight H plus 2. This one because we simply took this guy and further hit it with an L minus 1, so that we increase it further by 1. Or you can go directly from here if you use L2, L minus 2. And similarly, you can continue. If you have on the level H plus 3, there should be L minus 1, okay, let me try it just cubed. Or you can do L minus 1, L minus 2 on 0, or you can do L minus 3 on 0. So there, it's three-dimensional, this is two-dimensional, 1, 1. And these things are called levels. So this is kind of what I call level 1, level 0, this is level 1, level 2, etc. So level, where's the green, if I find it? Nothing. So level is the eigenvalue of L0 minus H. So I simply look at the conformal dimension and then subtract H. So that's why I get level 1, 2, 3, etc. Hence the whole Erma module decomposes like this. So note that there is no states that are above, because if I would try to hit this with L with a positive argument, then I get 0, because that's how the primary state works. It's killed by all L's with positive argument, positive subscript. So you cannot go up. There is nothing up there. So this is kind of the lowest level that you can get. And so the whole thing decomposes as a vector space into sum of levels. Where these are the subspaces of vectors of level L. 0, L1, etc., etc. And now one fun exercise that you can do is you can try to show, you can show that exercise. You can show that if you take the following function, the infinite product 1 over 1 minus q to the n. And this is the same as taking a sum of dimensions. So you can look at the dimensions of these things, like 1, 1, 2, 3, etc. And you can collect all these dimensions and put them as coefficients of some formal counting function, generating function. And you can show that at level L, the dimension is precisely the thing, the power of q that you get if you expand this thing and
So L and M are equal.
sorry?
L and M are equal.
No, because yeah, that's why I sorry, L and L. Oh yeah, sorry. Yes. Yeah. Okay, I guess this is probably a good point to stop for today. But so if you have any questions.
I'm a bit confused by how we define this vector space and how it coincides, like to define also this group action. And when using this group action, we use this continuity. But in these spaces, we can also say this space as a group action.
You can use, sorry. So this is only the, so Virasoro is a Lie algebra. So here I'm only describing the Lie algebra action. Okay. It's a Lie algebra which is generated by the Ln, and this thing an integer, and this one extra guy. And the claim is that these things determine the action uniquely. So if I say that this is the basis, if I say that I want the action to be such that on the primary state the generator act like this, and the rest can be determined by using the commutation relations until you end up with something of this. There is a more abstract characterization which I can write now because and so that's you can equivalently say that. So if you fix H and C, you can take, fix an H and C, and then define something that will call Virasoro plus. So this is the subspace of Virasoro which is spanned only by, this is the subalgebra spanned by L0, L1, L2, etc. Only those things. You can check that they close. You can check this is a subalgebra, and you can define, let's call it RHC, to be the one-dimensional vector space, or representation of this Virasoro plus, where the action of Virasoro plus is simply that let me throw in also the C hat. So this is the one-dimensional representation such that L0 acts by multiplying by H, C hat acts by multiplying by C, and everything else acts trivially. And L with argument bigger than 0 acts by 0. You take this one-dimensional representation and then you write that VHC is the universal. I think it's like this. These are HC. So you take the universal Lie algebra. Take the universal enveloping algebra of the given Lie algebra, which is that's a new algebra, and then you write things like this. This is kind of like an abstract characterization. You take like how does this work? So this thing is a. Okay, let me not comment on that further.
We're only the algebraic combinations of these things.
So this is again.
They're only like the abstract combinations of these things, right?
So
here.
Virasoro plus is it's the
Yeah.
algebraic combinations of these things.
Okay.
Then essentially the whole construction that I described here, how to act, all of this is just like follows. If you unwrap what this thing says, then it's just an abstract way to say what it works like this. But whenever you have something that's in Virasoro plus, then you should think of this guy as being the primary state, and this thing just tells you that whenever there is something that looks like this, you can actually move it to the right and then use the. Anyway, it's just the same thing.
Yeah, so from the construction, it is clear that we can pick up such M, for example, that LM kills like some chosen vector from the basis. For example, we want to kill that vector which is written on the blackboard, and we just take the M to be the sum of these n's plus 1.
Oh yeah, yes. So you're saying that if I have like a level, if I have a vector which is of a level L, and then if I act with it on something that's some
L plus 1.
L plus 1 for instance, or anything that's bigger than L, then it kills it. Yeah.
So what are the consequences of this? Or how is it called for representations, or is it somehow? What does it tell us about the representation?
I don't know what to say. It's just this.
Okay.
It's kind of, if you do representation theory of classical Lie algebras, then you don't have this, because then so the thing here is that these things go up to infinity, so there's infinitely many of them. So that's kind of what's special here. That even if you are at some finite level, there is always some high enough generator that kills the stuff. That's kind of maybe what's slightly different from the ordinary representation theory of finite dimensional Lie algebras.
I'm trying to make an analogy. So here, usually generators appear as charges in QFT, and they're like integration of some killing vectors, but it seems there's no integration here.
So for each of these conformal killing vectors, which are so you are in conformal field theory, you are supposed to have a symmetry, which is the conformal Lie algebra. So for each conformal killing vector field, you should have an element of the Lie algebra which acts, and these conformal killing vector fields they correspond to they will give you some combination of these L's. They will give you an element of Virasoro. Sorry, can you repeat the question?
Yeah, I'm just. So I noticed that it's not. We don't integrate over some killing vectors to get the charges. So.
Oh, you mean like integrate over a spatial slice or something?
Yeah.
Okay, let me think about that. That's let me get to you. That's a good question.
Thank you.
Any other questions? Or you are eager to go to dinner? Okay, then let's go to dinner.